This is the clock and program counter and the first of many parts of CHUMP, a 4-bit TTL breadboard computer. Right here, I have the first two main parts built. The first is the clock, which acts as the heart of CHUMP. It outputs a consistent pulse that can be referenced by any other part of the computer. It's composed of 3 555 timers and 3 logic gate ICs. The first of these timers is an astable mode, meaning that it can't remain in either of its output states, high or low, without naturally switching to the other after a period of time. The frequency of the outputted square wave can be calculated with this formula. Inside the 555 timer, there are two comparators which compare an input voltage to a threshold voltage decided by a resistor divider. When the input voltage reaches this threshold, it will change the state of an SR latch inside and discharge the external capacitor, flipping the output state. The second timer provides the monostable mode. It works similarly, except the trigger pin is wired to a button with a pull-up resistor so that the output is permanently low until the button is pressed, when the output will go high until the capacitor charges past the threshold voltage again. The third timer ignores the oscillating ability of the 555 and instead uses bistable mode, taking advantage of only the SR latch inside, where when the switch is in one position, the voltage at the trigger pin will drop to 0, and vice versa for the other position. The logic circuit afterwards is used to select one of the two modes, using the bistable 555 as input. The select input is compared with both clock mode outputs using AND gates, with one being inverted and the other not, so that each state of bistable 555 can select one of the two clock modes. These AND gates outputs are then passed through an OR gate, ensuring that either clock mode can reach the final clock output, and then a clock halt input is added to cut off any clock signal right at the end if necessary, that's just an AND gate. The second part is the program counter, and it's the first of many CHUMP parts that will use the clock signal as an input. Its role is to count in binary from 0 to 15, and eventually to keep track of the next instruction in the program ROM to be executed. Generally, it will increase once per clock tick, as it is right now, but if the load pin is pulled low, it will instead set whatever is on its input pins onto its output pins. In the finished CHUMP, this can be done only with two instructions, go_to, which jumps to an address in program ROM, and if0, which does the same, but only if the accumulator holds a value of 0. For this reason, a NAND gate is used on the load pin in the final build, whose inputs are a control bit, and a bit that is off by default and turns on only if a 0 instruction is being executed, only if an if0 instruction is being executed and the accumulator's value is not 0. To give some context to these instructions and the others in this table, I will briefly explain the purpose of each component of CHUMP. Each thick arrow in this diagram represents 4 bits of information, which is what makes CHUMP a 4-bit computer. The program ROM holds up to 16 instructions, each one composed of a 4-bit opcode, which controls which instruction will be executed, and a 4-bit constant, which is used in half of the CHUMP instruction set. The other instructions instead use a value from RAM, obtained using the read and load instructions. The control ROM interprets these opcodes into control bits, which are sent out all over CHUMP for various functionality. The multiplexer takes one of these control bits and uses it to decide whether you're using a constant from the low nibble of the program ROM or a value from RAM. This value is then passed on to the ALU along with a value from the accumulator, and it will do some arithmetic or logistic function with the two numbers. Here is a table of all possible functions the ALU can execute on two inputs, and here is a table of all the ones included in CHUMP. The result of this operation is then passed back to the accumulator. RAM holds 4-bit pieces of information from the accumulator, which can be read back into the ALU for more operations. The address register tells the RAM IC what address of RAM is being written to and read from, and whether it is being read or written. Finally, the program counter counts through the program ROM's instructions, moving on to the next one every time one is executed and jumping around for if0 or goto instructions. Here is a small program I've written to run on David Feinberg's CHUMP VM. It bit shifts a bit from the least to most significant bit, then loops. While it is a simple program, it serves as a test drive for most of CHUMP's functionality. It uses the accumulator, stores to RAM, executes ALU functions with constants and values from RAM addresses, has a branching path using the if0 instruction, which works because 8 plus 8 will wrap back around to 0 since the highest number that 4 bits can hold is 15, and uses almost all of the available instructions, barring subtraction. If all goes well, this will run on the final CHUMP build in December.